All right, section 3-5 is on displacement, velocity, and acceleration. The objective of this section is given the equation for displacement, find an equation for velocity and acceleration. If you recall back to chapter 1, you saw some problems just like this, where they gave you a displacement, and then the question was, what is the velocity at a particular point? And you had to realize that I'm given displacement over time, and it's going to require the quotient of those two, displacement divided by time, in order to calculate velocity. Since it's a quotient of a y divided by an x, that's a derivative that you were finding. And in other problems, they gave you velocity, and they asked you for the displacement. And in those problems, you had to realize that I've got to take the velocity and multiply it by time. That is, it's a product of y times x. And thus it was a definite integral that you were calculating for those problems. So those are the problems that we're going to see here in this section. Let's start out with a few terms that you need to understand here first. Not only understand the terms, but know the differences between some of these terms. So let's take a comparison here of displacement and distance. And we'll go ahead and define these here, which will help us understand, first of all, what each of them mean, and then secondly, what the difference is between them. So distance is a measure of how far an object traveled along a path. So if you're going from point A to point B, you have to actually take the actual path that you took to get from point A to point B, measure how long that is. The length of that path indicates for you the distance that you've traveled. On the other hand, displacement is a measure from the initial position to the final position of an object. So in other words, if you start at point A and you're going to point B, it doesn't matter what path you took to get there. You just have to measure how far it is from point A to point B. The length of that tells you the displacement. That's the difference between the two. Let's take a look at an example to kind of help illustrate that here. Our example is just going to use the number line to help us see this, but you could obviously represent this several ways. Let's suppose that point A is at 0 on the number line, point B is at 5 on the number line. And let's suppose that the path that we're going to take to get from point A to point B is the red line that you see there, the red arrows. So in other words, we're going to start at A, and we're going to head to the right. We're going to go past B all the way out to 8, and then stop, turn around, and come back to 5, which is where B is at, and stop. So that's the actual path. Now that path that you took, the length of that path tells you the distance you've traveled. So in other words, I can calculate the distance of this path here by taking the 8 minus 0. Again, our first direction there was heading to the right from 0 to 8, so the difference between those two tells me how far you've traveled. And then my second part of this path was to go from 8 to 5. So again, if I take the difference between those two, 8 minus 5, that'll tell me the length of that part of the path. So 8 plus 3 gives you 11. 11 is the distance you've actually traveled to go from point A to point B. On the other hand, you can see the blue arrow there is indicating the displacement. Displacement doesn't worry about the path that you took to get there. It just worries about where you started, where you ended, and what's the length of that path between A and B. And so if we measure the length between A and B, between your final and your initial position, 5 minus 0, that gives you a value of 5. So the displacement there would be 5. Okay, that's the difference there between distance and displacement. All right, the next two terms that we need to talk about are velocity and speed. And the definition of velocity and speed, there's actually several ways you could define these, but this is one way to do it. For velocity, velocity is the instantaneous rate of change of displacement. So the instantaneous rate of change, that's another way that we described a derivative. So it's saying it's the derivative of displacement. And now that we know some techniques to use to find the derivative of functions, we can come up with this velocity function. Another way to describe it is its speed and direction. The speed is the magnitude of your velocity. The direction is the sign, the plus or the minus, tells you the direction. On the other hand, speed, again, there's several ways you can define this. One way to define it, and probably the easiest way for us to work with it, is once we've calculated a velocity, I can take the absolute value of velocity and find my speed. So in other words, speed is velocity without direction. It's always positive. There's no plus or minus. Okay, so it's just the magnitude of your number, magnitude of your velocity. All right, one other term that we need to throw into the mix here is acceleration. And acceleration is the instantaneous rate of change of velocity. So again, it's the derivative of velocity. So if I start out with displacement, a derivative of displacement will give you velocity. And if I have velocity, the derivative of velocity will give me acceleration. All right, so as far as how these are all related, they're all related by derivatives here, basically. First thing we just said, if we call displacement here just some function x of t, which is how they'll usually define it in the book, they'll use the function called x, and my independent variable will be t for time. Turns out velocity, if we call velocity v of t, is equal to the derivative of that displacement function. It's equal to x prime of t. Speed, of course, we'll call that s of t. Speed is the absolute value of your velocity. So once you come up with your velocity, take the absolute value of it, you got yourself the speed. And then finally, the last piece to this puzzle here is acceleration. Acceleration, if we call acceleration a of t, then it turns out that a of t, of course, is equal to the derivative of velocity. That's how we defined it. It also turns out that because velocity is the derivative of displacement, I can think of it of acceleration as being the second derivative of displacement. Take a derivative of displacement once to get velocity, take a derivative of that a second time to get your acceleration. All right, so that's a nice relationship between those three there: displacement, velocity, and acceleration. All right, another term, or two terms that we need to understand is the difference between speeding up and slowing down. These deal with speed, and we need to understand how we determine whether an object is speeding up or slowing down, which can be a little bit tricky, but if you understand the relationship between these two terms and the velocity and acceleration, it's a piece of cake. Here's the relationship between velocity and acceleration and whether you're speeding up or your object is slowing down. Speeding up. You're speeding up as long as your velocity and acceleration have the same signs. So if your velocity turns out to be positive and your acceleration is positive, that means your object is speeding up. And the reason for that is because a positive velocity will get you moving in one direction, and then a positive acceleration increases that velocity as you go. Thus, you are speeding up. On the other hand, if you had a negative velocity, you're just going in the opposite direction is all that means. But if you have a negative velocity, or a negative velocity along with a negative acceleration, that means you're increasing that velocity in a negative direction. So you're speeding up in that backwards direction there. On the other hand, you're slowing down if velocity and acceleration have the opposite signs. So if your velocity is positive, that again means you're moving in one direction, we'll say the forward direction. And if the acceleration is negative, the velocity gets you moving in one direction, that forward direction, but the negative acceleration means that it's decreasing your velocity as you go. And thus you are slowing down. And of course the opposite is true if you move in the other direction. If you're moving backwards, that means you have a negative velocity. A positive acceleration means you're increasing that velocity, and thus you are slowing down. Okay? I should say you're increasing it back towards zero. You're slowing down. It was negative, and you're increasing it back to zero to make this object slow down. All right. One last thing here before we look at a couple of examples, and that's the second derivative. We already noted that when we were talking about acceleration a second ago. We said acceleration is the second derivative of displacement. But a second derivative is just simply the derivative of a derivative. And you can keep going with this, find a third derivative, fourth derivative, and so forth, depending on what you need to do for your particular problem. But a second derivative just simply means you take a derivative once and you get some new function called the first derivative. You take the derivative of that and you get yourself a second derivative, and so forth. So in other words, in order to find the second derivative, you first have to know the first derivative. You got to know all the derivatives prior to that one. Now there's several ways that we note a second derivative, the notation or terminology that we use to describe a second derivative. Just like we have a certain notation for representing a first derivative. So here's the first one, f double prime of x is the way we read that. Notice that we just add another little, looks like a single quote there, or it looks like a double quote, I guess, when we're talking about a second derivative. But those little quotes there that we're adding there, it's actually called a prime that we use to describe that. But you keep adding those to indicate more and more derivatives. If it's just y as your function to start off with, y equals something, and you want to find the second derivative, then we'd say y double prime. Just like we'd say y prime if it was just a first derivative. Here's one that gets a little bit tricky in understanding exactly what they're saying here, but remember, another way that we can indicate a derivative is d dx here, that d over dx, which we read as d dx. So a second derivative here would mean that you'd take the derivative of y, is how we'd read this over here on the left. If we put all that together, I can see that I have d times d in essence in the numerator, which is d squared. And the quantity dx is actually one quantity. It looks like two different variables there, but we're actually using two letters to indicate a single quantity there. So that's the reason why we write that as dx squared. It's the dx, and if you wanted to put it in parentheses, you could, but it's not necessary because dx is understood to be one thing. We just use two letters to describe it. Dx squared of y. So that's read as d squared dx squared of y. The key for us is to understand that those little 2's that you see in there that show up tell you how many derivatives you need to find. So if it's d cubed over dx cubed, I need to find 3 derivatives. If it's just d over dx, that was just one derivative. Here it's 2 derivatives. A second derivative. All right, and the last one here, we can kind of put all that together that we can take that we saw in that last one there. We can take the y and move it to the numerator and write it as d squared y over dx squared. So it's d squared y dx squared is how we read that off. Okay, those all mean find the second derivative. So those should be notations that we're comfortable with, that we're used to seeing, and just use them as needed in our problems. All right, so let's take a look at a couple of examples here. Look at example 2 there on page 95 in your book. It says the object in example 1 that they were describing moves in the x direction with the displacement from the y-axis given by this equation. So I'm going to go ahead and write that down. In fact, I'm going to write it in a function notation. X of t is equal to 3t cubed minus 30t squared plus 64t plus 57. And the domain that they've given you is for t greater than or equal to 0. All right, and it says where x is in miles, t is in hours. All right, so we'll use those units to help us get the right units on our answers. All right, so that is our displacement, or our position, sometimes we refer to that as. And so for part A, it says find equations for the velocity and acceleration. So let's go ahead and find a couple of derivatives. So velocity, remember velocity we said is the derivative of your displacement function. So it's equal to x prime of t. So that would give us, go ahead and follow your rules here for the derivative. Here we've got a sum of 4 functions that make up this original function. So just use your derivative of a sum property, which says take the derivative of the first function. The first function is actually a constant times a function. So our rule is the constant stays out front times the derivative of my function. The t cubed is a power function, so follow the power rule for its derivative. The 3 comes out front, t raised to the second power. We subtract 1 from the exponent. And then we subtract. Now the next function here is a constant times a function again, so the constant stays out front. And use power rule on the t squared there to get 2t to the first power. And then we'll add to that the 64t. Again, you've got a constant times a function, so 64 times, if you take the derivative of that t there, think of it as being t to the first power to help you out there. So it's going to be 1 times t to the 0 power. And then finally, the plus 57 is a constant, so the derivative of a constant is 0. All right, and let's just kind of rewrite that just a little bit here. So I've got 3 times 3 is 9t squared. 30 times 2 is 60t. And 64 times 1 times 2t to the 0, that's just 64. So there's our first derivative of our displacement function. Or in other words, it's our velocity. Let's do the same thing for acceleration. Acceleration, remember, is the derivative of your velocity function. Or you can think of this as the second derivative of your displacement function. So take the derivative of this. Again, you've got a sum of 3 functions here. Just take them term by term. That's our sum property. The first function has a constant 9 times your function t squared. So our rule is it's the constant times the derivative of the function. The function is a power function, so follow power rule to get 2 times t to the first. And then minus, here again we've got a constant times a function. If you want to think of that as t to the first to help you out here, write it that way. So it's 60 is the constant that stays out front times the derivative of t to the first. Again, use power rule, it's 1 times t to the 0. And then finally, the 64 at the end, that's a constant, its derivative is 0. So again, let's just rewrite that here slightly. It'll be 18t minus 60. All right, that's the first part of this question. Part B now says, find the velocity and acceleration at t equals 2, 4, and 6. And then it says at each time, state whether x is increasing or decreasing and at what rate, and also whether the object is speeding up or slowing down and how you decide it. All right, so let's just create a little table here to help us write all that down. So they've given us t values of 2, 4, and 6. So I'm going to start out with that here's my t values here. And I'm going to evaluate this at 2, 4, and 6. And they wanted us to find out what the velocity and the acceleration are. So we'll put our velocity and our acceleration. And once we figure that out, we can answer the other parts of this. So I'm going to use my calculator to help us come up with that. Grab your calculator, and we're just going to punch into y2 or y1 and y2. I guess if you wanted to put in your displacement function, you could put that in as well. But I'm going to just put in my velocity and acceleration for the time being, because that's all I really need right now. So take your velocity function, which we found out was equal to the 9t squared, or it's going to be 9x squared, obviously, as we type this in, minus the 60t, or minus 60x for us, and then plus the 64. And for y2, let's go ahead and punch in 18t minus 60, 18x minus 60. And I'm going to go to my table. I'm going to set it up in ask mode, so I can just type in the values of x that I want. And we'll go to our table. And they want us to calculate these at 2, 4, and 6. So 2, 4, and 6. And let's just write down what those values are. So we end up with, at t equals 2, we end up with negative 20 and negative 24. So this is negative 20 and negative 24. And at 4, it turned out to be negative 32 and 12. And finally, at 6, it was 28 and 48. Okay. Now we should indicate the units here as we're going through this. I'm just going to mark those at the top here of this. Again, remember that your time was in, what did they say it was in? I think it was hours. Yeah, it was in hours. So your time is in hours here. And our velocity, because we're taking the change in displacement, which is in miles, over the change in time, that's going to be miles per hour. Are the units here. And our acceleration, it's the change in velocity, miles per hour, over the change in time. So it's going to be miles per hour, or that's miles per hour squared. Okay. All right. Now the next part of this one asks to find whether x is increasing or decreasing, and at what rate. So we're just going to say x of t increasing or decreasing. All right. So we can determine whether a function is increasing or decreasing by looking at its derivative. If the derivative is positive, the function must have been increasing. If the derivative is negative, it must have been decreasing. So we got to look at the derivative of x. Derivative of x, remember, is our velocity. Velocity equals x prime. So look at the column here for velocity. And if it's positive, we're increasing. If it's negative, x was decreasing. So at t equals 2, the velocity was negative 20. So that means that we are decreasing, and we're decreasing at 20 miles per hour. Notice, by the way, that when we write that, we drop the negative sign, because when we say that we're decreasing, that accounts for that negative there. In fact, if you said you're decreasing at a negative number, decreasing at a negative number actually means you're increasing. So make sure if you're writing that out, you drop that negative sign there. Now for t equals 4, it's a negative 32. So again, we are decreasing at a rate of 32 miles per hour. And then finally, at t equals 6, it's a positive 28. So we're increasing at 28 miles per hour. Okay. And the last piece of this, the last bullet said to determine whether the object is speeding up or slowing down. So speeding up or slow down, we'll say. Just to abbreviate that a little bit. Now remember, to determine this, we have to look at both the velocity and acceleration. So over here, because the velocity at t equals 2, the velocity here is negative and the acceleration is negative. They have the same sign, so that means that we are speeding up. Okay? And then look at the next one here. At t equals 4, I can see that the velocity is negative, but the acceleration is positive. This is negative, but acceleration is positive. They have opposite signs, so that means we are slowing down. And for the last one there, I can see that they are both positive. They have the same sign at t equals 6. That means that this thing is speeding up. Again, the key there is you have to look at both acceleration and velocity to determine whether you're speeding up or slowing down. Don't look at just velocity. You can't look at just acceleration. It's both. All right, look at part C on that. What's this? It says, at what times on the interval from 0 to 8 is x at a maximum? And is x ever negative if t is in this interval? All right, so to determine that, the question is, when in the interval from 0 to 8, when is x at a maximum? So if you look at a function, I'm just going to sketch just some function here. It doesn't really matter if it's this function or not, but if I have a function that hits a maximum, notice that at that particular maximum that my slope there is 0. If I draw the tangent line there, I can see that the slope is 0 at a maximum. And that's the key for us. Now it turns out that you can also have a slope of 0 at other points, but the way that I'm going to determine whether this is a maximum or not is to find out where the slope is 0. I should say the way to find the maximums are to find out where the slope is 0, and then use that to help me figure out if it's a maximum or not. All right. Realize that if I have a minimum, the same is true there, that if I continued this graph, for example, that here at this minimum, the slope equals 0 there as well. So in other words, just by finding a minimum, or excuse me, just by finding a slope of 0 does not guarantee me a minimum or a maximum. I have to look a little bit further into it to figure out which one of the two it is. All right, so that's the type of problem that we're looking at here and what we want to do. And so we want to find out where x has a maximum. So I need to find out where the slope of x is 0. In other words, the slope is the derivative, and I need to find out where that's equal to 0. So we need to find out where the derivative of x prime, is equal to 0. Of course, x prime we've already found. That was actually v of t. So we're really trying to find out where your velocity is equal to 0. So let's take our velocity function that we calculated up here, which was 9t squared minus 60t plus 64. 9t squared minus 60t plus 64. And we want to set that equal to 0. Now you can find that solution many different ways. I'm going to go to the graph to find out where that velocity function hits 0. It's a quadratic function. We have a quadratic formula. You could use that to help you find those zeros as well. But I'm going to use the calculator to help me do this. And again, this is your work, just saying that you're going to set that equal to 0. And by all means, you can use your calculator to help you solve that equation. So let's go back. Oops, I want to go and graph this thing. And let me get a decent window for this before I start sketching this. They're talking about the interval from 0 to 8. So I'm going to change my window from 0 to 8. And really, I'm only interested in the velocity function. If you wanted to sketch the original function along with it, you could go ahead and do so. But I'm going to sketch just the velocity function. And so I'm going to look at a table of values to help me figure out what the corresponding range should be here. So I'll set up my table to start at 0 and increase by 1. And again, y1 is my velocity. So it looks like it starts out at 64, and then it becomes negative for a while, and then it becomes positive, goes all the way back up to 85. So it looks like if I go somewhere from a y value of negative 50, it looks like, all the way up to somewhere around 90. Looks like that, oops, I'll set my scale to 10. Looks like that should give me a pretty decent sketch of this derivative function. I said I was only going to sketch the derivative, and I actually have both functions still sketching here. So let me shut off the acceleration function. This is really all I need to see. All right, so there we go. I'm trying to find out where my velocity function is equal to 0. That's where I'm crossing the x-axis there. So let's just calculate those zeros. If you go to second calc, you can find those zeros. Looks like that first 0 is somewhere between 1 and 2. So I'm going to give a left bound of 1, a right bound of 2, and I'll give it a guess of like right in the middle there, 1.5. We get 1 1/3 actually, so I'm going to call that 4/3 actually is where that's at. T equals 4/3 is our solution there. All right. Now the other solution that I need to find is somewhere over here further to the right. We'll calculate that, 0. So that one looks like it occurs somewhere between 5 and 6. I'll give it a left bound of 5 and a right bound of 6. And again, I'll give it a guess right in the middle there. And it looks like it's at 5 1/3. All right. 5 1/3 is 16/3 if you want to write it that way. I guess it's up to you how you want to write those out. If you want to write 1 1/3 and 5 1/3, that's fine. I'd write them in a fractional form there, though, for sure. All right, so those are my two solutions. But what I've got to figure out now is which one of these is the maximum. So if you look at the graph that we are given for the velocity function roughly looks something like this here. And again, this is at 4/3 and this was at 16/3. This is our velocity. And the question is, where does x have a maximum? So without even seeing the sketch of x, I can still determine whether or not, or which one of these is a max, or if either one is a max. And I can do that based on the fact that I know my velocity function is positive. I'm positive right here. I'm above the x-axis for that section of the curve. So if my function is positive, my derivative is positive there, my velocity is the derivative of displacement, that means my original function must have been increasing. And it increased to a point where I hit a maximum right here and got a slope of 0. And then I can see in this section of it, the next section of it, I'm below the x-axis. So my function must decrease there. In other words, I know that my sketch of my original function must do something like this. It must increase to a maximum and then start to decrease. And then here at 16/3, I am going to hit a slope of 0 again. And because my function is now, my derivative, I should say, is above the x-axis at this point, that tells me that my original function must be increasing. And so that's a minimum at 16/3. So I have a maximum right here at 4/3. That's my max. And I have a minimum right here at 16/3. So to answer their question, x of t has a max at t equals 4/3. And if you were to sketch the original displacement function, you would see that that's the case. All right. It says, it also asks there, is x ever negative if t is in this interval? And so you could take a look at the original function and evaluate it at this minimum over here at 16/3 and see if you actually get a negative value. Let's check out what happens there if we do that. If we calculate x of 16/3, the reason I'm using the 16/3 is because that's the minimum. That's the lowest it ever gets here. And if I plug in 16/3 into my displacement function there, you can punch it in your calculator and check to see what value you get. But when you do that, you're actually going to get 1/9. Very, very small number. It's really close to 0, but we're still above 0. So because at the lowest point we're still above 0, that means we're never negative. So x of t is not negative. Okay.